In this section, we're going to look at power consumption in an AC circuit. Now, this can get a little bit complicated. So we're going to try to do as much of a conceptual approach as possible, but it becomes very important to think about something called the phase angle, which again, if we go to our phasor diagram, the phase angle is the angle between the voltage vector and the current vector. Okay, so let's look at power in an AC circuit. I'm going to start with the simplest type of object, first of all, and that is power consumption in a resistor. And if we remember from earlier, when we did this for our DC examples, it was really quite simple. We said that the power dissipated was equal to the current times the voltage, and alternatively, this could be written as I squared R. Well, the same thing is going to take place for the instantaneous power, which is being used. So what we're seeing here is if the current is oscillating, the power consumption is also going to oscillate too. Now, we come into a little bit of difficulty here because when we're looking at the current, it is based on a sinusoidal function. It's based on sine or cosine, depending on where we start with the phase of the voltage and the current. So what we want instead of an instantaneous power, because that doesn't really help us, it's always changing, we want to look at an overall average of the power that's being used over a finite amount of time, over a reasonable amount of time. So we're going to look at, once again, our power. We have power is equal to current times resistance. We know that the current fluctuates as a function of time. We have this current going back and forth. But remember, the direction of the current doesn't really impact how the power is being dissipated. Okay, if it's going forward or backward, current is negative or positive, we're going to dissipate the electrical power and turn it into heat. So makes sense that when we square this, that our function of sine, which goes positive and negative, only takes a positive value. Okay, for instance, if we take the sine of 270 degrees, we know that's -1. If we square that, that becomes 1. So this part of the function right here is always going to be a positive value because we're squaring it. Okay, so now let's do this. Let's calculate the average power, and we're going to do this by integrating it over time. Okay, we're going to integrate it over time. Normally when you think about taking an average, you think about taking the sum of all things and then dividing it by the number of things. And really an integral is a sum of an infinite number of infinitesimal elements. And that's what we're going to do here. So we take this integral, and again, this is going to be constant, so that can actually go out front. We're going to integrate sine squared. And if you integrate sine squared, you find out that it's actually equal to something very simple. It's actually just equal to 1/2. So what this tells us here is that the average power is actually going to be 1/2 the peak power. Okay, so when taking the average power, we can say that I0, that's the maximum power, is going to be equal to twice, I'm sorry, I0 squared. It's equal to twice the RMS current. So I can actually replace that in here. Okay. Now, graphically, we can actually see that this works. That the RMS current is the maximum current divided by the square root of 2. How did we get that? That again comes from RMS squared is equal to I0 over 2 squared. Okay, you take the square root of both sides, you get this result. And that's why with the RMS values, we quote the RMS values whenever we're dealing with AC power to calculate things like the average power and other things. So for instance, when we talk about AC power, we don't talk about the peak voltage, we talk about the RMS voltage. Okay, so again, you can see this graphically. Here is my current graphed as a function of time. You can see it's a sine function. There's equal amounts above and below the axis. So if I take the average of this, I'd have 0. But we're not taking the average of I, we're taking the average of I squared. So if I square this function here, the valleys become peaks again. And it looks like this, okay? And now we're taking this area, integrating over this area, actually over one period. And again, if you look at this, the total area here is going to be, basically, 1/2 the peak squared. Okay, so basically what we're saying here, what I'm trying to say here is that if we integrate I squared, where small I is occurring as a function of time, and capital I 0 squared is the peak. If we integrate this, we get 1/2 the peak, which again is the RMS current squared. Okay. So again, I wanted to concentrate on the concepts here. Here is our equation for the power. We can either take the peak current and the peak voltage multiplied by 1/2, and that gives us the average power. Or again, we prefer to take RMS values of current and voltage and multiply them. The product is equal to the average power. But think about what's happening here. If we follow the energy, and conservation of energy is very, very important. We get electrical energy in from whatever AC source that we're using. It could be a generator, it could be from the grid, by plugging into the outlet, whatever. We are putting energy into the system, and energy per unit time, of course, is power. So as we put energy in, that energy is dissipated as heat, as the resistor converts the electrical energy into thermal energy. Okay, so a resistor is a very, very simple thing. Just like with the DC circuit, we put a resistor connected to some EMF. This EMF just happens to be oscillating with respect to time. It is going to convert the electrical energy into thermal energy. Okay, so that's the simplest case that we have here. And again, just to remind you, the power that this resistor is going to consume is equal to the product of the RMS current times the RMS voltage. Okay. Now, what happens when I put a capacitor or an inductor and I connect that to an AC power source? Again, I'm talking about something that's idealized. I'm talking about a capacitor where there's no resistance in the wires hooking up the capacitor. I'm talking about an inductor where there's no resistance in the wires of the inductor. Again, an inductor is basically, an electromagnet, if you want to think about it that way. Now, what we're going to find out is in a pure capacitive system that the energy that we put onto the capacitor is going to be equal to the energy that comes off the capacitor. So there's going to be a net flow of 0 power. We put as much power onto the capacitor as it's going to dump back into the system. Again, when I mean pure, I'm talking about no resistive losses. because the resistive losses are just P equals I times V. For an inductor, a pure inductor, I'm sorry, I squared R. I got to be careful there because some of the power can be doing other things too, as we'll see. For a pure inductor, once again, energy is dumped onto the inductor in the form of a magnetic field. And then as that magnetic field dissipates, it has to put that energy someplace and it dumps it back onto the source. So the really interesting thing here is that the power for a pure capacitor or an inductor, the net power, the average power over time is actually zero. And this is going to have very significant consequences for different power systems that we hook up to the grid. Okay, now, can we actually show that the power in a capacitor over time, averaged over time, is zero? Okay, what we have here is we have a plot. The voltage is shown in red, okay, and our current is shown in blue. Okay, I'm going to use the lowercase symbols to indicate that these are changing as a function of time. And as we said before, if we want to calculate power, okay, power is a function of time. The instantaneous power is just I times V. Okay, so I take the product of these two, and for a capacitor, I note that the voltage lags the current by 90 degrees. Okay, so if I multiply these two functions together, what I get is this green function. And this is really, really important. Notice here that sometimes the power is positive, okay? So the area is positive, and sometimes the power is negative. Now, what exactly does that mean? Well, it means for these positive peaks, I am loading up the capacitor with charge. For these negative peaks, I am unloading the capacitor. Okay, so that's why my power is zero. I'm putting as much power into the capacitor as I'm getting out of the capacitor. Because what is the energy going to be converted into? Okay, the energy has no place to go. So it just simply returns to the system. So if I look at this, I'm going to see that I can come up with a new expression for power, okay? That the power is equal to the current RMS times the voltage RMS, and this is the important change we're going to make, times cosine of phi, where phi is the phase angle. That's the angle between our voltage and our current, okay? Now for the resistor, that was zero. So the cosine of zero was just 1, and our power was just current times RMS. Current RMS times voltage RMS. But now what we see here is that the cosine of this 90 degrees, cosine of negative 90 degrees, in fact, is zero. So my net power for this capacitor is going to be zero. Okay, so again, up here, that's the power that's in. Down here, that's the power that goes out. Add the two together, net power is zero. Okay, so I mean, the capacitor is doing what we would expect it to, right? A capacitor stores energy in the form of an electric field. So the capacitor for an alternating voltage is going to fill and unfill, sort of like a bucket. Okay, so we fill it up and it unfills, and we fill it up and it unfills. So a capacitor really, if there's no resistive losses, doesn't use up any power in the system at all. Okay, so keep that in mind. We'll think about that later on as we talk about motors and how they affect the grid. Now, our inductor. We're going to have a very similar situation here. The main difference that we have is that the voltage leads the current by 90 degrees. So, instead of not negative 90 degrees, we have positive 90 degrees. Again, calculating the power for the system, our phase angle is 90 degrees or pi over 2 radians. So when I do my calculation again, cosine of 90 degrees is 0. So the whole power is 0. And again, think about conceptually what's going on here, okay? When the inductor is building up its magnetic field, it is taking in energy, okay? So the power is positive. But as the magnetic field dies out, it produces an EMF, a back EMF. It'll dump that back on to the circuit, okay? And then the magnetic field builds up, and then the magnetic field dies down again, okay? So if I simply had a solenoid sitting there, and just like the capacitor, it's hooked up to the circuit, just like the capacitor, we're going to say that there's no resistive losses. That is going to absorb energy and then dump the energy back, okay? The net result is 0 power usage. Okay. Again, visually, if you want to think about what's going on, energy goes into the system as the magnetic field builds up, okay? And then as the magnetic field dies out, because it's going to oscillate, okay, it'll go back to the system. All right. One thing that I didn't talk about, by the way, a capacitor and an inductor can actually give off energy even without resistive losses. I can do this in the form of broadcasting electromagnetic waves. So this we'd have to completely contain the magnetic field to prevent it from broadcasting, but that's a totally separate thing. We're going to just treat the inductor like, okay, converts electrical energy into a magnetic field energy, and then that magnetic field energy gets dumped back onto the system. Now, in the real world, we have devices that can convert electrical energy into work. And of course, these are motors. And one of the most common motors is an induction motor. And an induction motor has, as its name implies, big electromagnets in them, which act as inductors, okay? So for a motor, again, in many ways, it acts like an inductor. For a motor, it takes energy in as the magnetic field builds up, but some of this energy will leave in the form of work because, well, that's the whole goal of what the motor is supposed to be doing. It's supposed to be doing work, okay? But some of the energy will return because, again, it's acting like an inductor. So the magnetic field dies out, it's going to produce this back EMF. It's going to dump that energy back on to whatever energy source that we've hooked there, okay? So this actually creates a problem, all right? This actually creates a problem for us. You plug in a heater, no problem. Electrical power is turned into thermal power. You plug in a capacitor, it'll store the energy very briefly, then it'll dump it back on. But for a motor, okay, only some of the energy that we put into it is going to be converted to work, and other energy is going to be dumped back into whatever circuit or in many cases the power grid, and we're going to have to do something with that. Okay, so in a real power system, what we tend to do is we tend to take energy in because that motor, after all, is doing work, and most of the power goes into turning those electrical motors, but some of the power is going to be backfed into whatever power source that we have. Okay. Why is this a problem? Why is this a problem? Well, again, when we're operating an electric motor, we want all the electrical energy to be turned into working power, stuff that we can use. The electrical power that's sent back is what we call non-working power. And when we look at a motor, we look at the system, okay, this slight difference, okay, now it's not going to be quite 90 degrees, so we're not going to send back as much power as we take in, but this phi is not going to be perfectly zero. So and again, here's your phase angle. We call cosine phi the power factor, and that tells us how much working power we get for the amount of actual power that we put in. And this is important because, okay, think about the grid, okay? Now, I know it shows a high tension wire here. This is probably more like a transmission line or a substation, okay? Think about the grid. The actual power that makes the motor go is our working power. The non-working power is sort of the back feed that comes from the motor. I'm not sure that that's a proper term here, but I'm sort of using that. It's the backflow of energy back into the system. And the power companies will charge large users if their power factor is too low, which means that if you end up using like only 85%, that'd be a power factor of 0.85. You only use 0.85%, 85% of what you take in terms of electrical power compared to your total power, you are going to get a surcharge. So here's what the power company can end up charging you. And it depends on the power company. It can even depend on the time of day. They will charge you not only for the working power that you use, but they will charge you for the non-working power that you send back. In addition, they may even, on top of that, send you a surcharge if your power factor is too low. Typically, if you drop below a power factor of 0.9, the power company gets upset at you and they're going to surcharge you. And the reason they do that is because the transmission lines have to carry both forms of power. So, for instance, let's say that you take in 10 kilowatts of working power, okay? That's the actual stuff that you want. But you send back, I don't know, I'm just going to make up some amount, 2 kilowatts of non-working power, okay? So what does that make your power factor? Well, that's 10 over 12. I think that gives you like a power factor of 0.8. That means that the system has to handle now 12 kilowatts of power, where only 10 kilowatts of power were actually being used to do anything, because the transmission lines themselves, due to their resistive heating, they can only take so much current before they have to shut down. Same with the substations. So what many electrical providers will do, many grid operators will do, is they'll sort of like surcharge the power users if they have a really poor power factor, because they end up sending too much energy back. And there's a real reason for this. It's not just the power companies being greedy. They have a limited number of capacitors and substations to make up for some of this power load. So what they're trying to do here is you are creating a large amount of inductive reactance on the system, okay? And we have to balance that with capacitive reactance. All right, we'll talk a little bit more about impedance and all those other things later on. But when we calculated impedance, we saw that the impedance actually had the inductive reactance and the capacitive reactance as being a difference. And for this particular case, they have to add capacitors so that the phase angles don't get too far out of whack. During the summertime, especially when a lot of people are using air conditioners, they're going to have to use more and more of these capacitors in the substations to balance that load out. It's interesting because blackouts that have been caused during heat waves are not really just people wanting to use too much energy, okay? It's a combination of people using too much energy, okay? Too much working power coupled with too much non-working power coming back, because again, these substations can only handle so much, based on how much capacitance that's installed there. So what is one way that a large company, which is using, huge induction motors to, air conditioner their building or on the factory floor, what is one way that we can eliminate the surcharge? Well, one way to do this is at the site, instead of relying on the power company to use capacitors at their substation, okay, install your own bank of capacitors to balance out the inductive load of your motors, okay? Now, you never can completely compensate for all of the non-working power, but one way of thinking about this is the power company is sending energy into your system, okay? The motor takes in this energy, converts it into work, and then it tries to send this backflow of energy, backflow of electricity or power. And instead of going back to the grid, it goes to this capacitor where it's stored, and then the capacitor dumps it back into the motor when it discharges. And these power factor correction units really reduce the amount of power that we require on the grid, because again, the power companies, they just want to send the energy out. They don't want the energy coming back toward them because it doesn't help them. Okay? It just means that they have more power flowing over their lines. So these power factor correction units, which are actually big banks of capacitors, here you can see relays, breakers, and other things. Here are the big capacitors right here. They will, help correct for the phase between the current and the voltage. When we think about, what in fact is taking place here, just go back here. Ideally, you want your voltage, okay? You want your voltage as in phase with the current as possible. I did a terrible job drawing that. I have my peaks, valleys, peaks, valleys, peaks. There I go. You want the two to be in phase as much as possible. And that keeps the power flowing in one direction. Okay. Now, one way of thinking about this is there's a beer analogy. I'm not a drinker, so it's sort of an interesting analogy to use. Power factor, again, is a ratio of how much it's like efficiency. It's how much useful power you use compared to how much non-working power you use. So let's say you order a beer, okay? You want as much of that glass to be filled with beer as possible because that's what you ordered. The foam on top of it is completely useless, okay? It's not anything, it's just taking up space right there. So in the beer analogy, the power factor, when you have this non-working power, it's sort of like a beer glass that's filled half with foam and half with beer, okay? You're paying for something that's completely useless, okay? In a more efficient system where the load is balanced, there's less foam, there's more beer. Okay. And again, you could get to the point where if the phase angle became 90 degrees out of phase, you couldn't deliver any power at all. As the phase angle approaches zero, the efficiency of the grid becomes better and better. So again, during really, really hot weather, there aren't many items, aren't many appliances, aren't many systems that have a lot of capacitors, okay? Most of the systems, most of the power load that we have are big motors, big electric motors, which have big magnets that act like big inductors. So the challenge during high peak loads is that the users are not just using a lot of power, but these loads are large inductive loads. And the largest users of power have these power factor correction units, but at home, you're just plugging your air conditioner in. You don't have anything fancy like that to improve this. So, again, these inductive loads can bring down the grid, even when the grid has enough capacity to power everybody, okay? What happens again is the phase between the voltage and the current becomes further and further away, and this can do damage to our substations. This can do damage to the generators, and this is why we tend to have blackouts, because the power company has to shut down different elements of the grid. Okay.